Hello everyone, welcome back. In this video we're going to talk about what we call the double angle formulas or the double angle identities for our trigonometric functions. It doesn't take a whole lot of effort to derive these formulas since we already have our sum and difference formulas for our sine and cosine function. So I want to take a minute to go ahead and see where these formulas come from. And so the first one we can derive is going to be our double angle formula for our sine function. So we're going to find a way to express sine of 2 times an angle or sine of 2 theta in terms of sine and cosines of the original angle theta, or you can think of that as the half angle. And the way we can generate this formula or identity is just going back to our sum formula for our sine function, which I have on the board up here, and setting both a and b equal to the same angle, setting both a and b equal to theta, right? Because then we'll have theta plus theta, which gives us 2 theta. So we just need to use the sum version of our formula on the right-hand side. So we use that plus sign for the top symbol there, and then set a and b equal to theta. And so when we set a and b both equal to theta, just plugging them in directly gives us sine of theta times cosine of theta plus cosine of theta times sine of theta, but the order of multiplication doesn't matter, so we can think of these as like terms and combine them together, and that allows us to write this as 2 times sine of theta times cosine of theta. And so that gives us a very helpful and useful formula, our double angle formula for our sine function. We now know sine of 2 theta is equivalent to 2 times sine of theta times cosine of theta. Well, now for our double angle formula for cosine, both a and b will be equal to theta. So that'll give us that cosine of theta plus theta, or cosine of 2 theta, is equal to cosine of theta times another cosine of theta minus sine of theta multiplied by another sine of theta. All right, but we can rewrite this and simplify this, right? Whenever we have repeated multiplication, we can use our exponents to rewrite that. And so we see that cosine of 2 theta is equivalent to cosine squared of theta minus sine squared of theta. So now we do have a double angle formula for our cosine function, but there's actually a couple different versions that we can write down for this particular double angle formula. And the way we can discover these other versions of our double angle formula for cosine is really just by using our Pythagorean identity in combination with the formula that we already have. Remember, our Pythagorean identity for our trig functions, at least for our sine and cosine functions, says cosine squared of theta plus sine squared of theta is always equal to 1. So we can take this identity and rewrite it in a couple different ways by moving the pieces around. And so if we're starting at cosine squared plus sine squared equals 1, we can either subtract sine squared from each side or cosine squared from each side to solve for the other function. So from that we can see cosine squared of theta is equivalent to 1 minus sine squared of theta, and sine squared of theta is the same or equal to 1 minus cosine squared of theta. So if we keep that in mind, we can replace this first term in our first double angle formula for cosine with 1 minus sine squared. So this cosine squared becomes 1 minus sine squared of theta, and we still have to subtract away our other sine squared of theta term. But now we have some like terms, and we can rewrite this as 1 minus 2 times sine squared of theta. And that gives us another version of our double angle formula for our cosine function. And so we do have one more version of our double angle formula for our cosine function. That other version is going to allow us to write cosine of 2 theta in terms of just cosine of theta. And there's a few ways we could go ahead and derive that version of our double angle formula. We just have to replace sine squared with 1 minus cosine squared, and it doesn't matter if we do it in our original version of our double angle formula or in that most recent version. So let's go ahead and just do it from that original version. So we're keeping our cosine squared of theta, just copying that first term down, but now we're going to make a substitution and replace that second term, sine squared of theta, with the quantity 1 minus cosine squared of theta. Remember, all of this is still equivalent to cosine of 2 theta, and now we can simplify this a little bit more. We have to be careful when we distribute that negative sign though, because what happens is we get a minus 1 and then actually a plus cosine squared of theta. That gives us 2 cosine squared of thetas. And then we can't forget that constant term of minus 1. So that is our third version for our double angle formula for our cosine function. lets us write it in terms of just cosine of that single angle theta. And it says cosine of 2 theta is equal to 2 times cosine squared of theta minus 1. All right, so in this example, we're going to see exactly one way in which we can apply our double angle formulas. So this example says if sine of theta is equal to 5/6 and we're told theta is in quadrant 2, we want to find the exact value of sine of 2 theta. So if we want to find sine of 2 theta, we're going to have to use our double angle formula for our sine function that says sine of 2 theta is equal to 2 times sine of theta times cosine of theta. We already have our value for sine of theta. We know that that is equal to 5/6. To finish this problem off, we just have to find that value of cosine of theta. To help us find our value for cosine of theta, we can go ahead and use some right triangle trigonometry. So we're going to go ahead and interpret this first piece of information that tells us sine of theta is equal to 5/6 in terms of a right triangle. So theta is the angle in our right triangle of interest. And remember, our sine function gives us the ratio of the opposite side to the hypotenuse. So the side opposite of our angle theta must be 5, and the hypotenuse of this triangle could then be 6. And so now if we finish setting up this right triangle, we can go ahead and use it to evaluate our cosine function, remembering that in terms of right triangles, cosine is the ratio of the adjacent side length to the hypotenuse. So that means we have to find the adjacent side length to our angle theta here, and that's just done using our Pythagorean theorem. We know the hypotenuse squared would give us 36. And if we subtract away from that the square of the other known side, subtract 25 away from 36, we get 11. And so just solving the Pythagorean theorem for that last side length, we find that it has to be equal to exactly the square root of 11. And so there is one more piece of information that's actually necessary here to make sure we get the correct overall value, and that's that piece of information we haven't used yet, the fact that our angle theta is in the second quadrant. So that's where we have to take our right triangle trig, and remember that we can also interpret this in terms of the unit circle, because remember, in the unit circle, if we're in the second quadrant, cosine is like our x coordinate for that point on our unit circle. And in the second quadrant, we know our x coordinates and our cosine function will have to be negative. So I did not draw this little reference triangle if you want to think about it that way in our second quadrant, but we can still make that adjustment. If we want to end up in the second quadrant, we have to have that cosine or x value be negative. And so that means the adjacent side to our right triangle, which kind of represents our x value, would have to be negative square root of 11 instead of positive square root of 11. Now that we have our right triangle set up, we can find the exact values of sine and cosine from them, although we already know our exact value for sine of theta is 5/6. That was given to us from the start of the problem, but we should verify that using our right triangle as well. Remember, SOHCAHTOA says sine is opposite over hypotenuse. That gives us 5/6. We also can now use our right triangle to find the exact value of cosine of our single angle theta. Remember, cosine is the ratio of the adjacent side length to our angle to the hypotenuse, and that'll give us negative square root of 11/6 for cosine of theta. Well, now we are ready to use our double angle identity for our sine function since we have those necessary pieces of information. We know that sine of 2 theta is going to be equal to 2 times our sine value for theta, which is 5/6, multiplied by our cosine value for theta, which is negative square root of 11/6. And so now we just multiply those factors together. We get our final answer for sine of 2 theta is negative 10 times the square root of 11/36. Or if we reduce that fraction by canceling out that common factor of 2, our exact value for sine of 2 theta is negative 5 times the square root of 11 all over 18.